Πρώτος ομιλητής είναι ο κύριος EinB Bahnfleth, όπως είπαμε και πιο πριν, καθηγητής στο Πανεπιστήμιο της Πενσιλβάνιας στο τμήμα της Αρχιτεκτονικής και πρώην πρόεδρος της άστρα, πρόεδρος της άστρα για το 2013-2014. Το θέμα που θα μας παρουσιάσει είναι το High Performance Buildings. Mr. Bahnfleth, please.
Well, thank you and good morning again. I took this topic that was suggested, high-performance buildings, and have a few thoughts for you that hopefully will tie together some ideas that I believe are important in implementing this concept. The first thing that I think we should do is consider what we mean when we use this term. We have many phrases that are common in our built environment jargon, and sometimes we forget what the definition was behind them when we use them too often. So to me, a high performance building has a number of characteristics. You can find these in other places. This is a list that I made up based on my own impressions. First of all, to go back to my earlier point, they begin with superior indoor environmental qualities. You can't have a high performance building that does not provide a very high level of comfort and promotion of health and productivity for those who occupy it. The second thing is that it should be resource conserving. So this gets to the issue of the efficiency of our buildings, using as little water as possible, using as little primary energy as possible. We often focus there more than on the first point. They must be low polluting, so we increasingly are concerned with the environmental pollution of all types that are generated by our buildings. It really began, actually, I think, in my recollection with refrigerants and their effect on the stratosphere, but now it's also carbon emissions and the effect on climate and particulate matter and the effect on health. In case you've not seen the World Health Organization estimates, 7 million people a year die from PM 2.5 pollution that is associated with fossil fuel combustion primarily, and a lot of that is from buildings. So this is a very important current issue. A high-performance building is one that will also be durable and resilient. The idea of sustainability is that things last a long time and we get a long investment out of the materials that we put into them. And they should be maintainable. We don't get performance from a building unless it is designed to be maintained over its lifetime. I don't need to tell stories here about how buildings can deteriorate, because I'm sure that everyone is familiar with what happens if we don't keep up installed systems so that they maintain their intended level of performance. And they should be economical. Frequently, I find, particularly in the U.S., where things are very much driven from a commercial point of view, that cost is the single most significant barrier to making progress in the area of high-performance buildings. Everyone is very concerned about minimizing their investment and getting a quick return on it. So we need to focus on that too as a practical matter. And really the most important thing is that high performance is actualized, and this is to the point that no matter how well conceived a building is or how well constructed initially, if we don't do the things to make sure that it actually continues to produce high performance, then it really isn't a high performance building. It's simply a building that might have been or that was. I want to review a few points here with respect to each of these different characteristics. Indoor environment, this means broadly thermal, air quality, lighting, and acoustic characteristics of the environment. We know now from many years of research that have accumulated, quite credible research, that indoor environmental quality affects the health of people in buildings, it affects their productivity, and affects their learning ability. Unfortunately, if we look at the way that standards, even for high-performance buildings, are written today, there is not, to my way of thinking, as much recognition of that research or as much implementation of the findings of it in those standards as there should be. The standards today are based largely on what we would call personal acceptability. The indoor air quality is good if the occupants of the building don't complain about it, that lighting is good, if it's subjectively viewed as being acceptable, and so forth. We have plenty of evidence that if that is the approach you take, that you don't get optimal results, particularly where air quality is related to things like learning ability and productivity. Fisk from the U.S., from Lawrence Berkeley National Labs, has tried to quantify what we are not realizing in terms of benefits of good indoor environmental quality, and he published that in a short ASHRAE journal article that is worth reading several years ago. And his conclusion was that there are avoidable indoor environmental quality issues in buildings in the U.S. that could save the country as a whole over $300 billion a year, which is roughly the total amount that is spent on energy for buildings in the U.S. in a given year. So this highlights the relative importance of IEQ in economic terms. That's why I always put it at the top of the list of these criteria. And there is a very close link between indoor environmental control and energy use. If we look at buildings in the U.S., which are not unrepresentative of other developed parts of the world, over half of the energy that goes into the building is for environmental control, and nearly half is for HVAC, which is the primary concern of ASHRAE and related organizations. So there's a very tight connection here, and if we're going to be concerned about saving energy, we have to recognize what we're using it for and start with the right criteria for indoor environmental quality in our buildings. With respect to the objective of being resource conserving and low polluting, this is where we begin by redesigning the building in an integrated way. We need to start by reducing the demands for artificial environmental control. So it's a bit ironic that an organization that started out to promote mechanical equipment for buildings really today needs to take the point of view that we need to make the requirements to use the systems that we design as small as possible by managing solar loads, by managing thermal transmission through the envelope of the building, by maximizing the potential for natural ventilation and daylighting, which bring us into very close cooperation with architects. Some of these goals of reducing demands can only be realized if we start at the beginning and have the form and the orientation of the building optimized from an architectural point of view, and then we can deal with it from a mechanical systems point of view. And increasingly, water is something that is a major concern. I just happened to watch a very good documentary on the water issues that are developing in the U.S. before I came here, and was struck by how close we are to having really critical situations in some of our most populated states like California. Droughts continue, demands continue to go up. With respect to being low polluting, I think we all know how to approach that through efficiency of systems. We reduce pollution, first of all, simply by requiring less energy of the type that produces it. Natural and hybrid ventilation will reduce our dependence on primary energy, daylighting, and also more sophisticated techniques like using more hydronically based heating and cooling systems that require much less transport energy than the all-air systems that many have been designing and specifying for years. And then, of course, to that we add renewable energy, whether it's on the site, whether it's at the community level, or whether it's the grid. So the role of photovoltaics and solar thermal and wind also come into play with regard to this point of reducing pollution. If we are as successful as Germany appears to be in implementing solar energy to replace conventional energy. Eventually, we're going to run into some very interesting issues with balancing the grid, and I think that will be one of our next challenges when we see how interconnected everything is when we're trying to deal with those sorts of large load variations. Durable and resilient simply means built for long life, adaptable to changes in climate. This is something that is starting to be considered by standards writing organizations. If we're writing a standard for energy design of a building to last 30 years or 50 years, should we be considering climate change over that period of time? And we should also consider the protection of the occupants of buildings from hazards both of natural and man-made type. This was something that became an issue for ASHRAE after 9/11 in the U.S., and some good work was done on standards and guidelines for making buildings more resilient in that sense, but my impression is that that has become something of a forgotten issue for the time being, but there are reasons to give it higher priority than it's received. To make buildings maintainable, designing for maintenance means picking equipment that is easily maintained, selecting materials that are going to be durable, designing for good access, something that too often isn't done, having controls and instrumentation that are maintainable, and emphasizing simplicity. Over what's now becoming a fairly long career, I've become more and more convinced that the way to success is generally by working in the direction of the simplest solution, rather than always trying to conceive of a more complicated way to do things. That often results in systems with a lot of potential and not much performance. And the importance of maintenance planning and having good processes for maintenance is also something that we should consider. ASHRAE has a very good standard for O&M that is not as widely used as it should be. With respect to economics, one of the key questions is who receives the value of an investment. Often we say that something ought to be done because it makes sense on a life cycle cost basis, or it's good for a society, but most of our economies are set up to reward individuals for their investments, and so the questions of who pays to upgrade an asset and who pays to operate it is important, as well as how long it's occupied. So when we seek solutions that will give us higher performance buildings, we have to consider how the investor is going to be compensated in a fair way for doing that, and make that part of the process. There's not an easy solution to that, but it's a clear barrier that needs to be overcome. And now to the point of actualizing performance. We get performance when we have good design, plus evaluation of the building after it's operating, plus the maintenance that needs to be done based on the evaluation. If we don't have post-occupancy evaluation and maintenance, then we find that buildings do not perform well. And for as long as I have been working in the field, which goes back to the 70s and 80s now, it's been widely accepted that if we simply fix the controls on the average building, that we could realize 15% improvement in energy efficiency at almost no cost. So there is a lot of what would be called low-hanging fruit there to be gathered simply by keeping things up to the level they were intended to be. So commissioning at the point of delivery of a building is the process that starts with the design intent and goes through the occupancy of the building initially is important, but also retro commissioning for buildings that weren't commissioned, and continuing commissioning for those that may have been commissioned. If we don't periodically review the performance of the building, then we're not going to be able to have confidence that it's actually doing what it was intended to do. For processes of design, the integrated process will be the one that's required, a linear process of design that many are accustomed to won't work. And by linear, I mean the architect designs the architecture of the building and hands it to the structural engineer, and the mechanical engineer puts mechanical systems in it, and then the electrical does power, and we get some lighting, and at every step we lose some opportunities to realize better performance. There are lots of sources of guidance on this integrated process. ASHRAE's standard 189.1 for high-performance green buildings lays out in many respects what this process would look like. And we also have rating systems like LEED and the other sustainable building standards that are used around the world. But these generally do not have the characteristics of true standards, and really, from my point of view, don't make good guides for how we should act. There's something that we apply after the fact to give a building a rating on how well it performs. But the good standards are there to be used. And they cover design, they cover construction, and they cover plans for operation, which are all critical to real performance. Commissioning is a good place to start. ASHRAE 189.1, the Green Building Standard, requires commissioning, so we see that it says there has to be acceptance testing, and commissioning is required in Section 10 of the standard for buildings of a certain size, and a whole host of systems need to be commissioned as listed over on the right-hand side of the slide: HVAC, envelope lighting, fenestration, irrigation, plumbing, and so forth. So comprehensively verify that these systems are performing as they were intended. The first green building that was installed built on my campus is the architecture building at Penn State. Was supposed to have a rainwater recovery system that turned out to not be functional when the building was finally delivered. If they had commissioned that properly, then perhaps they would have made corrections to it that would have made it usable, but now it simply is a monument to an unrealized aspiration for that particular building. Not much can be done about it after the building has already been constructed. Retro-commissioning is something that is needed for existing buildings. And of course, most of our buildings are existing buildings. The turnover of new construction is getting smaller and smaller in the developed world. So in the developed world, it's important to focus on making our existing buildings, some of which greatly predate the era of sustainability, operate as well as they can. So the benefits of retro-commissioning have been demonstrated to resolve problems that may have gone all the way back to the original design or construction, and to fix problems that have accumulated over the lifetime of building, resulting in energy savings, energy and non-energy cost savings, better IEQ, and increased value of the asset. So one of the references that I've seen that has made an attempt to look at the value of retro-commissioning is this one by some folks from Lawrence Berkeley National Laboratory and also Texas A&M University in the U.S., which has done many studies of existing buildings, and they estimate energy savings of almost up to $1 per square foot, would be $10 per square meter of energy, and nearly half that much in non-energy savings for buildings that are retro-commissioned. So that's a very significant improvement. A very typical building in the U.S. might have an annual energy cost of $1 per square foot, $1 to $3 per square foot being the range. So if you can make an improvement of 70 cents, that is quite a big improvement relative to the total energy cost for that building. And in terms of the cost of doing the retro-commissioning process, it's quite affordable if it's done properly. You see total costs of 13 to 45 cents per square foot compared to 2 to 3 times that in potential savings. And so from a simple payback point of view, an estimate of 0.2 to 2.1 years, which even commercial interests would think is a good return. If we're a government entity, they will often accept paybacks of 10 years or longer. So it really makes no sense to fail to implement some kind of process like retro-commissioning for existing buildings. I should also mention here specifically energy certification, since this is an energy conference. Disclosure programs are becoming very widespread worldwide, even in places where we tend to avoid regulation as much as possible, like the U.S. In the U.S., the Energy Star program is being used in conjunction with a growing number of disclosure laws, most of which are implemented by cities, not by states or by the federal government. And ASHRAE has a program called Building Energy Quotient, BEQ, that it began developing in 2009 that is now starting to see more common use than it did in its first few years. The idea of energy certification is to recognize the value of energy efficiency in order to make the public aware of the value of efficiency, to let owners know how their buildings are performing so that they'll want to improve them if it's feasible to do that. And as part of the certification program, typically we would also require that opportunities for improved efficiency be identified. And also certification adds greatly to what we know about how the building stock actually performs. We have a surprisingly small cross-section of knowledge of how buildings perform of various types when we dig into the details. These programs also on the larger level, as data is accumulated, will allow us to document the effects of programs to improve efficiency, and we develop in the process a workforce that's more aware of efficiency and able to provide it to buildings. So this is a map that shows where the U.S. stands with respect to energy certification laws. California, New York, and Washington have been three of the most progressive states, and in particular, New York City and Seattle and San Francisco have very good programs. The rest of the country is slowly coming along. Chicago and Philadelphia are two recent large cities that have added disclosure ordinances. At this point in the U.S., we're mainly reporting energy use. The question ultimately is going to be, if you don't measure up to a certain level of performance, is that going to lead to a requirement that buildings have to be fixed? And opinions are divided about whether that's something we should do or something that we shouldn't do, but I think it would be helpful if there were some kind of requirement to remediate. It's a personal opinion. The effect of these programs is that now almost 6 billion square feet, the 600 million square meters of mostly commercial floor space in the U.S. falls under a disclosure law, and that is increasing all the time. In Greece, of course, you have a program, and some of the participants in this conference have been very involved in evaluating it. This is a nice paper reporting on the early results of the certification program in Greece, and you can see here the ability of a certification program to document whether changes that are implemented in codes and standards are actually having an effect. And it's good to see that for both the residential and non-residential buildings, the effect of laws that have required more insulation and higher efficiency of components in buildings have had a significant effect since the 1980s over all 4 climate zones. I want to mention also in wrapping up this talk that a good way to learn about high performance is to read case studies of actual buildings that report data, and this is one of the things that ASHRAE has tried to do through its High Performing Buildings magazine. This is not a commercial because we're not selling it, we're giving it away. You can go to the ASHRAE website and look at all of these case studies free. It's a quarterly magazine that documents the performance of real high-performance buildings around the world. You'll find buildings in China here. We're actually starting a Chinese version of this journal next year. And for many types of occupancy, from single-family residences to schools to laboratories to office buildings. So as an example of a building that was profiled in high-performing buildings within the last couple of years, Manitoba Hydro's office building in Winnipeg, Canada. It's a corporate headquarters for 2,000 people and has 695,000 square feet of conditioned space, and it was constructed at a cost of about $400 per square foot, which is not an excessively high cost for commercial property of that type today. And here are some of the things that were reported in the case study. Sustainability features, low-use plumbing fixtures and rainwater capture. 24% of the materials in the building were recycled materials. It's designed for daylighting. There are individual controls for all of the offices, which we know tends to give the occupants more of a feeling of comfort and satisfaction with the environment. It has demand-controlled ventilation, hybrid natural ventilation, and to reduce carbon emissions, a geothermal heat pump system for heating and cooling. And over on the right side of the slide, you see the energy summary of the building. Annual energy use intensity of 29.3 kBTU per square foot per year on the site. For the U.S., that number for a typical building is more like 90 kBTU per square foot per year across all the climate zones. So that's really a very good performance. And if you look down there, you can see that it performs at 60% of the energy use, the energy cost budget of a building for Manitoba, and at only 52% of the energy demand of a building that meets ASHRAE Standard 90.1 2007, which is a standard that's widely used as a benchmark for high-performance buildings.
Maybe 10 more minutes. Thank you.
And here is a figure that illustrates how in this northern environment they have been able to take advantage of natural ventilation during the cooling season. You see availability there of up to 90% of the time in June for natural ventilation, so very effectively used in this building. And daylighting also very effectively implemented. Here is some data that show the daylighting in comparison to the energy demand, and you can see the flat demand during the middle of the day that indicates that they're getting a good offset of electric lighting through the daylighting systems in this particular building. So that's the large end. And another very interesting profile that you can find here is at the complete opposite end of the spectrum. This is a case study of a Sears and Roebuck kit home. I don't know whether you're familiar with that idea, but for a while in the U.S. it was possible to order a house from Sears, the department store, and they would ship all of the materials to you, and you could build it on your site. And that was an inexpensive form of home back at the turn of the 19th century. They've become somewhat collector's items. So here was one, a fairly large one, 3,600 square feet, that was built in Concord, Massachusetts in 1915. And it was decided to do a deep energy retrofit on it because of its historical value and to make it ready to last for, as they said, another 100 years. So they spent $83 a square foot on the renovation, which is a fairly high cost, but this was a no-holds-barred renovation where they put in higher performance equipment than some might based on purely economic considerations. And yet, at the end of it, when they saw how the building performed, they concluded that if they had a 4% interest rate effective and the current gas costs, it would be revenue neutral. And if we consider the likelihood of energy costs increasing in the future, that there would probably still be a good return on investment for this building over time. Because it's a home, Most of the most important changes had to do with the envelope, so the windows were replaced. They were probably single pane glass in the originals. A lot of work was done to tie together the different envelope systems. We've seen recognized in recent years through building science research that some of our biggest problems occur because we don't join the different control layers together at the connections in the building. So wall to roof, roof to foundation, and to floor, and so forth. Drainage plane continuity was implemented, which removes a lot of concern about water damage and mold growth. Air barrier continuity was implemented that reduces the infiltration and the loads associated with that, and the thermal insulation was extensively redone as well. On the mechanical side, a condensing boiler was put in to replace conventional equipment to do both heating and domestic hot water, and a high-efficiency air conditioner was installed that had forced ventilation. It's very uncommon in homes in the U.S., although we have a standard 62.2 that specifies mechanical ventilation for homes to get acceptable air quality. And heat recovery was implemented with the ventilation, and also MERV 13 filtration. I know ASHRAE standard 52.2 is not the one that you would use in Europe, but the higher the MERV number is, the more efficient the filter is. Currently, ASHRAE standard 62.1, that's the basis of a lot of the codes in the U.S., specifies only a MERV 8 filter. So 13 is just a few notches below HEPA and would have a very good impact on removing particles of a size that could impact health. And here is a quick summary of the energy use of the building. Over on the left-hand side, you see the original energy use of the building in terms of millions of BTU per year, source energy, and the actual use of the building is over there, the real world source energy use, electric and gas, just over 100 compared to the original 375 or so, so a tremendous reduction in energy use, and the possibility to make the home nearly zero energy with photovoltaics added is shown in the far right of the bar. So those are a couple of examples of case studies of this type, and I think the more of these that you read and see what kinds of measures have actually been effective, the easier it will be for you to apply those ideas to your own projects.
5 more minutes.
So to conclude, I'll try to stretch this slide out to 5 minutes.
Perfect.
Yes. High performance means a lot of things, but I'll say one more time that IEQ is the place to start, and then we do all of the other things that are also important. High performance design has to be integrated. You see in both of these examples that I have presented that the envelope and the mechanical systems have to be, and the lighting systems have to be designed to work together. You can't use daylighting, you can't use natural ventilation in that Canadian office building if the form of the building has not been designed to take maximum advantage of it. That's one of our biggest challenges today, is that we've spent many years allowing architecture to depend too much on artificial lighting and on artificial space conditioning. We need to start going back in the other direction to integrate our designs so we minimize those demands first and then meet them efficiently. If we're going to have actualized high performance, if we're really going to have buildings that work, then we're going to have to invest in monitoring them, evaluating them, and taking action based on the results of those evaluations. Retro commissioning, in particular, even for existing buildings that weren't commissioned, that weren't designed as high performance, can have very beneficial effect and is something that should be considered. Energy certification can help if it leads to action. I think my concern about mandatory certification programs that don't have a requirement to act is that they're simply honored to the extent that we turn in the data, but if we don't do anything about it, then we haven't accomplished very much. And the final message would be that from an economic point of view, as you can see from both of these examples and many others that you can read about in high-performing buildings and in other venues, it is economical. High performance pays, and if we start from the point of view that we understand and believe that it's realizable, then I think we'll have a very positive impact on the performance of the building stock and make a real contribution to solving some of these problems with energy supply, water supply, and quality of the atmosphere that all of us hope to succeed in addressing through our professional work. Thank you.
Okay, we have 3 more minutes, so are there any questions? Okay, thank you, Bill.